Hello, everyone. My name is Eshanta Mishra. I'm a senior sales engineer at Synspective. And today I'm going to be talking about my company, Synspective, and how we use synthetic aperture radar technology to monitor offshore wind parameters. So my presentation will be basically divided into these two sections. First, I'll give a brief introduction of Synspective, who we are, what we do. And then I'll give a detailed overview of how we use SAR technology for monitoring offshore wind and waves. So without further ado, I'd like to start with the introduction of Synspective. So Synspective is a Japanese startup which was founded in 2018. And in the past 4.5 years, we've been able to raise around 200 million US dollars in funding. And we have a very diverse team of more than 180 members who come from around 29 countries throughout the world. And we're also the recipients of several national and international geospatial awards. And regarding what we do, we manufacture our own synthetic aperture radar satellites, which we call Strix. So Strix is the name of our satellites. And we operate these SAR satellites and acquire SAR images using them. We then sell the acquired SAR images as raw data itself. And we also combine the SAR images acquired by our own satellites, the SAR images acquired by other third-party satellites, as well as other Earth observation data to develop and provide analytical solutions to our clients. And regarding our satellites, we've already launched 3 satellites so far. 2 of these satellites are currently in orbit. So we recently decommissioned one of our satellites, and we have a 4th launch coming soon in a few months. And ultimately, we are aiming for a constellation of small SAR satellites. So with this constellation of small SAR satellites, we plan to achieve a revisit rate of around 2 hours globally. And with our current generation of satellites, we are able to provide up to 1,000 square kilometer coverage within a single image. So yeah, that concludes my introduction of Synspective. And next, I'd like to talk about how we are using SAR technology to monitor offshore wind and wave parameters. And before we do that, I'd like to introduce about some other solutions that we are providing. So basically, in addition to our offshore wind assessment solution, we also provide solutions in the areas of land displacement monitoring, forest monitoring, and damage assessment for different disasters. If you want to know about these solutions in more detail, please feel free to reach out to me or visit our website. So next, I'd like to talk about our offshore wind and wave assessment solution. So within our offshore wind and wave assessment solution, which we also call OWW solution, we measure 3 main parameters. And first is offshore wind speed. So we measure the offshore wind speed. And next is the detection of wind wake effects. And the third one is the measurement of wave heights. So next, I'd like to talk about the concept of SAR-based wind estimation. So on my left, you can see an image of when there are fewer waves in the ocean, or in other words, a light wind is blowing over the ocean surface. In these cases, when microwave is emitted by the SAR satellite, these microwaves, they get reflected away from the ocean surface. And because of this, barely any microwave returns back to the satellite. And these regions have low backscatter intensity, or in other words, they appear darker in SAR images. And contrary to that, whenever the ocean has more waves or a strong wind is blowing over the ocean surface, in these cases, when microwave is emitted from the SAR satellites, these waves, they get scattered in different directions. And because of that, significant amount of waves return back to the SAR satellite. And because of this, these kind of areas, they have higher backscatter intensity or they appear brighter in SAR images. And next, I'd like to show some images of how actually oceans appear in SAR images. So the image on my left, it is taken from European Space Agency's Sentinel-1 satellite. And these dark regions in the image, it represents oceanic areas. And if you zoom into this red square box in the image, we can clearly see wind turbines in wind farms present in this area. And on my right is an image taken with our own satellite, Strix Alpha. And if you zoom into the area shown by the red box in the image, we can clearly see some distinctive wave patterns in the ocean. And these characteristics of how oceans appear on SAR images help us to calculate different wind parameters. And next, I'd like to talk about our wind speed solution and some characteristics of SAR-based wind speed estimation. So with SAR satellites, we can get representation of real-world wind speed variations that occur at a given location at a given time. And using SAR satellites and SAR technology, we can provide high-resolution wind speed maps at around 10-meter height above the sea level. And this helps us to understand the wind flow due to different features of the site, such as the site-specific topography, the presence of man-made structure, or the other artifacts in the ocean. And regarding satellites, we currently mainly do analysis using European Space Agency Sentinel-1 satellite or our own Strix satellite. But we also have the ability to use some other third-party SAR satellites as well, if that is required. And we've done some accuracy evaluation of the results generated using Sentinel-1 as well as Strix satellite by comparing the results from these satellites with the data obtained from MetMast. And we've got a root mean square error of around 1 to 2 meter per second. But please bear in mind that this accuracy can be significantly improved if we integrate our SAR data with other data sources such as MetMast data or data from buoys. And regarding revisit time, with Sentinel-1, you get a revisit time of around 5 to 12 days. It means that one area in the ocean can be revisited by the satellite again in 5 to 12 days. And with Strix, depending on the location where the site is located, we can get a revisit period of daily or up to a few hours in the future with our satellite constellation. And regarding the availability of historic data, with Sentinel-1, we can obtain wind characteristics or wind parameters from 2014 to present date. And with Strix satellite, you get the data on a demand basis. So it depends on location to location and the availability of images for that location. And using Strix for wind speed analysis, we can get data with high temporal frequency, again, depending on the location, and less bias compared to other satellites that we've analyzed. And these are some examples of outputs that can be generated using our solution. So on the leftmost is a high resolution wind speed map generated using our algorithm. And you can clearly see the variation in wind speed, these gradients that represent the variation in wind speeds. And on the center, you can see the wind speed data from our satellite overlaid with wind direction data for that location. So you can also understand in which direction the wind is flowing and what is the variation in the wind speed. And in addition to that, we also provide statistical variation of wind speed. So in addition to instantaneous time stamped wind speed, we also provide wind speed variation annually or monthly. So you can see how wind speed is varying for a given year or for a given month. And we also provide viable statistics of the variation of wind speed, which is pretty much common in the industry. And this is the comparison of our wind speed data generated using SAR satellites with simulation and reanalysis data. On the leftmost part, you can see data from ERA5, which is reanalysis data. On the center, you can see simulation data from Global Wind Atlas. And on the rightmost part, you can see data from SAR satellites. So data from SAR satellites clearly shows the different gradients of variation of wind speed. So you can get a more detailed visualization of how wind speed is varying locally in a given area. And on ERA5, the resolution is around 30 kilometers, whereas for Global Wind Atlas, the resolution is somewhere between 200 to 300 meters. With SAR satellites, you can get resolution all the way from around 3 meters to whatever resolution is required for your specific use case. So these are some comparison of data from SAR satellite with reanalysis data and simulation data. And next, I'd like to talk about our solution of detecting wake effects. And before I do that, I'd like to show this map of wind farms in the North Sea. So each polygon in this map represents wind farms that have already been built in this area or are in the process of being built. And as you can clearly see from this map, there are a lot of crowded wind farms present in this area. And with wind farms being constructed very close to each other, it gives rise to wake effects. So wake is basically the reduction of wind speed and increase in turbulence downstream of the wind turbines. And on my left, you can see an aerial photograph of wake effect, where you can clearly see that there is some turbulence in the wind turbines present downstream of other wind turbines. And on the right, you can see wake effects visualized in our own Strix image, so image taken by our own satellite. And next, I'd like to show some analysis results of how wake affects the wind speed in a given area. So on my left, you can see the wake effect on downstream of the wind turbines present in that area. And on the image on the right, you can clearly see some wake effect trends in wind speed analysis for this area. So the image on the right, it has this wind farm called Dantisk, which was there in the site before 2015. And another new wind farm called Sandbank was constructed in the same area somewhere between 2015 to 2017. So if you look at the image of 2015, there is no clearly visible wake trend or any reduction in wind speed trend. But if you look at the analysis result after 2017, downstream of this wind farm called Sandbag, you can clearly see the reduction in wind speed. So this is because of the wake effect, and we are able to detect this using our algorithms. And next, I'd like to give a very short introduction of our wave height estimation algorithms. So we use some advanced machine learning algorithms to estimate significant wave height from SAR images. So these plots, they show the comparison of wave height estimated using our SAR data and the wave height from COSINA, which is the Coastal Observing System for Northern and Arctic Seas. And from these plots, you can clearly see good correlation between the SAR data and COSINA data. So we also provide wave height data in this manner. And next, I'd like to talk about some common application of our OWW solutions. So most of our clients use our offshore wind and wave solutions for wind farm site planning, for planning of different logistics, for procurement of offshore wind towers and turbines, for procurement of ships, and for procurement of like other materials related to the offshore wind sites. They also use our solution for installation and construction of offshore wind facilities, for repair, operation, and maintenance of these facilities. And some of our clients also use our solution for decommissioning of offshore wind facilities. So next, I'd like to talk about some differences between our product and other publicly available data. So many of you might be aware that there are some publicly available SAR wind speed data as well, but our solution differs from those publicly available data in these four main aspects. So first is the ability of our algorithm to integrate with other data sets. So we have the flexibility in what kind of input we feed to our algorithm. So we have the ability to integrate our SAR inputs with data from other sensors such as metmast, buoys, or other kinds of ground measurements or some other client data. And with this integration of other data sets with SAR data, we are able to increase the accuracy of our wind speed calculation, as well as extrapolation of point measurements from this metmast or buoys to a larger area. And our next value lies in the point that we have flexibility in the output we generate using our algorithms. So we are able to provide flexible resolution output maps based on our client requirements. And in addition to individual timestamp data, we are able to provide aggregated time series data as well. So like I mentioned earlier, you can also visualize the monthly and annual variation in wind speed at a given site. Our next strength lies in the fact that we are able to provide extensive quality control of the results. So we have some advanced algorithms that help us remove the influence of shapes, different kind of slicks, bathymetry, etc. from the results. So you get good quality results that have not been affected by these factors. And our next value lies in the fact that we provide a localized analysis for each area of interest. This means that we take into account site-specific characteristics such as bathymetry of that site and other factors, rather than providing one global map that fits all areas. So these are some values of our product compared with other publicly available data. And finally, I'd like to share about our overall solution concept, how we deliver our data to the clients. So our solution starts with us taking SAR images from our own satellite streaks or other third-party satellites such as European Space Agency Sentinel-1 or other satellites. We then take some simulation meteorological data, and we can also combine it with ground measurement data if it's available. And we feed all of these data to our algorithm. We then obtain statistics for wind speed, for wake area, and wave height. And these data can be delivered to our clients through our own platform where we visualize these data if that's required. Or if it is required, we can also deliver these data through API to our client or partner services. So yeah, that basically concludes my presentation. Thank you very much for your attention.